2, 1, welcome back. So understanding quadratic factoring through graphing. If you're going to be working with quadratic factoring or just quadratic expressions, any kind of equations, doing the factoring is one thing. What I'm going to try to do in this video is to give you a visual of what this factoring that you're doing actually means visually, kind of in a two-dimensional graph. Now, I have about 5 examples here. Now, not all of them are quadratic expressions, and you can hopefully know which ones are quadratic and which ones are not. So that's the first test. The first expression that you have, this one right here, is not a quadratic. This is basically just a linear equation. So it looks like it is in the slope-intercept form if I would write this out as, y is equal to 3x minus 9. So that's not a quadratic. What makes it a quadratic is, of course, that the highest order is a square. Now, which ones are quadratic? Well, this one is a quadratic because of the fact that it has a square, which is the highest order. This one would be a quadratic. This one would be a quadratic. This one would not be a quadratic. This one has a 4, which is the highest order. Now, on the right-hand side, I've actually factored these things out. So I'm not interested in trying to explain factoring here. I'm trying to tie in, once you do factor, how does it relate back to an actual graph? If you're interested in trying to factor these things out, I'll put up a link up above if you have forgotten and you want to know the tools. Now, there are different videos that you can watch. Now, I have tried to cover here not just quadratics. The first one is, as I said, so that's just an equation of a line. And I have taken a few special quadratics. For instance, the one which is the fourth one, that's a perfect square. It is a quadratic, but it is a perfect square because notice that we have the same 3x plus 5 appearing 2 times. I've also taken the difference of squares as well, and that is for the last one. So I'm trying to capture all the different variations here, and I'm going to start graphing these things out to show you visually what they mean. Now, let's start with the simplest one as kind of a review, right? Which is, graph a line, and that is the first one. If I take this thing, of course, I can graph it in many different ways. I can graph it just through using a table of values, where I can substitute values for x and then get a y, or I can use the slope y-intercept form. So here is my slope, here's the y-intercept. And if I graph this thing out, I will have a relationship between the x and the y. And that's what I want to be able to see. Like, what is this relationship? Now, on the top here, you'll notice that I actually factored this out as well. So it factored. Let me copy and paste it. And that's what it equaled. And once I factor it, I get 3, because I factored out the 3, because it was common to both terms. And I got x minus 3. Now, this right here is not really in the slope y-intercept form anymore, but that's okay. I want to be able to first start off with graphing this. If I take this line, let me graph it here for you. You should be able to know how to graph lines, because if you're watching this video, the assumption is that you have now probably are either in grade 9 or grade 10, and you've already graphed lines in general. And I will use Desmos, which is one of the nicest tools on the web, and hopefully it will be free for a long time. So y is equal to 3x minus 9. And this shouldn't surprise us in any way, that it's basically just a line. The y-intercept is negative 9, so it goes through negative 9 right there as I zoom in. The slope is 3, so it has a positive slope. It goes up. Now, what I wanted to show you here is, I wanted to draw your attention not to the y-intercept, so not to the negative 9, but notice where it crosses the x-axis, which is at 3, right? So it crosses the x-axis at 3 here. Now, why am I drawing your attention to this? I'm drawing your attention to this because when you put things in factored form, notice I have here 3 and then it's x minus 3. There is something special about a factored form, this right here. What does it mean to have an x-intercept? What it means to have an x-intercept is that is where y was set to 0. If you have an equation like we do right here, y, and you set it to 0, and now you get 3x minus 9, or in factored form, 3x minus 3, like this, then you notice something special about this particular setup right here. The x-intercept on the graph was 3. Now notice, if you set this thing equal to 0, meaning y is equal to 0, and you try to solve for x, you indeed will get x is equal to 3 when y is equal to 0. When this is 0, we get our x-intercept, and that's going to be the point 3, 0. And notice how nicely it is captured by this factored form. That x minus 3 right here, x minus 3, if you set that to 0, you move this over on the other side, you will get x is equal to 3, which is the x-intercept on our graph. And now, through all of the different types, doesn't matter if it's quadratic or not, if you're going to start graphing them, you will notice that your lines, now this is just a straight line, but when it's quadratic, it's no longer going to be a straight line, then you will notice that these factors that we have, so all of these different wonderful factors that we have, actually are the x-intercepts of your graphs. Now those x-intercepts, when we take the actual expressions, so if I take now the second expression right here, and I say y is equal to x squared plus 5x minus 36, I'm going to take this one, and I'm going to do the same thing as I did with the line. Now, of course, you might just be starting in grade 9 or grade 10 to try to graph some of these relationships, but the relationships are not always linear. They're not always just straight lines. They might be quadratic. And if I take this, so I'm going to paste this, so this is like my relationship between x and my y, and what happens to that relationship. Again, you can use a table of values for x, you can start plugging them in, you'll get a bunch of points, and then you can substitute those points in, and then you can slowly start to see the relationship between on a graph. Now, because we have the tool like Desmos, we can actually graph it directly, and we'll see something which is wonderful. Now, the factored form for this particular expression and the relationship here, so I'm going to bring this down here, and I'm going to show you that something, again, special has happened. So please pay attention to this 9 and then to this 4 right here. Because again, just as in the previous example with the line, 3x minus 9, we're expecting that these 9s and 4s will show up somewhere in terms of your x-intercepts. Let's try it. This is x squared plus 5x minus 36. I'm going to go back in here. Y is equal to x squared. And this was plus 5x. And actually, let's just double check. And minus 36. Minus 36. And now I'm going to zoom out here. You're going to notice something. So that green is no longer a line. Now it's some kind of a quadratic, and that's what it is there. That's the actual graph that we have of that particular quadratic. But notice where it intercepts the x-axis, right? The x-axes are intercepted. Maybe let me remove this one. So one of them is at -9. That's where it intercepts one of them. The other one is at 4. And, well, check that out. When you have it in factored form, then indeed, and you set your y is equal to 0, what you would get is, so right here, if you set y is equal to 0, and it is in factored form, x plus 9 and x minus 4, Well, there's going to be two places for x that will make this equation equal to 0. Well, one of those will happen when you have x plus 9 is equal to 0. And if you solve this, this is going to happen in x minus 9. And the other one, this one right here, is going to happen when x minus 4 is equal to 0. And now if you move that to the other side, you're going to get this. And notice that indeed, those are the two places that your graph will intercept the x-axis that you have. Now, when you're starting this off, you may not necessarily know exactly how this graph looks like. But what you will know is if you ever have a factored form, then these, which we actually call the roots of the equation, so the roots of the equation, or the actual physical things that happen is they are the intercepts, your x-intercepts, but you may be hearing them eventually in terms of roots. Those are the roots where you have y is equal to 0. And that's very, very interesting to be able to note. And that's the beauty of having the factored form for quadratics or anything else for that matter. Let's take a look at another example and see if this is actually true. And now these things are getting harder and harder here for us. And I'm going to take this, now the next equation right there, or expression, and then the factored form. So let me copy this, bring it down. I'm going to bring it down right there. Now let me remove that. So these are exactly the same. Now this is an expression, but what if I changed it to a relationship between y and x? So I changed it into an equation now, which is a relationship between x and y. And now what I would try to do is, okay, so what if I try to graph this? Now, you can start to deduce the fact that the factored form, so there is going to be something special about these two factors that we have. And now, again, if you set y is equal to 0, then what that should mean is that there's going to be two roots to this equation because it is a quadratic. This quadratic, this 2, tells you that it will have two roots, two places where you can find y is equal to 0. And where do they happen? They happen at 3x minus 4 when you set that to 0. So if I solve for x here, I'm going to solve this by moving it to the other side. It's going to become positive. I'm going to divide by 3 on both sides, which is going to give me 4 over 3, which in decimal form, I guess, is 1.33333333. So I'll put a bar over that. That is telling me that what I'm going to have is 1 over 3 bar 0 is going to be one of the intercepts. And that 1 or 4 over 3 is the first root of that particular equation. The second one is going to be 2x minus 5. If you set that to 0, and now you play around with it, so meaning I'm going to switch this and isolate it for x, it's going to be 5. I'm going to divide both sides by 2. I'm going to get 5 over 2. Now this one's a little bit nicer. It's going to give me 2.5. That is your second place where the graph is going to intercept the x-axis. So I have two roots, 4 over 3 and 5 over 2. And let's graph this. So 6x squared minus 23x 20. (6x squared) minus 23x plus 20. I believe that's what it was. Let's double check. Minus 23x plus 20, correct. And now, notice that it looks very similar to the other one, which is kind of, it's called parabola per se. That's what we call it. You're going to start learning that a little bit later on, but that doesn't matter at the moment. Right now, just want you to see that the quadratics and what the meaning is of that factored form. And here, so if I zoom in here, so notice that one of them, you can start seeing it, that if I keep zooming, at 1 point, 33333, okay, so that point right there, okay, is your intercept. So that's mapped right there. Now your other one should be 2.5. And indeed, notice that it is exactly 2.5. That is what happens to all of these expressions in factored form. And if you would graph them, it's very nice to be able to practice that on your own to get some kind of a concept and understanding of what these things mean when they're in factored form. So that was another example. Now, if I continue this, you can probably start guessing. So here, now this is a perfect square. Copy, and let me paste it right here, and we're going to see what happens to this. So this is going to be interesting because of the fact that what I have is I have 3x plus 5 multiplied by 3x plus 5. That's what the perfect square is. Now here, if I set this y is equal to, so I have a relationship like this, I can start thinking of what will happen. What does this mean? That the graph will cross, right? It will cross the x-axis, I guess in two places. It has two roots because it's a quadratic. But now, how can it cross in the same place? So this is the beauty of being able to see this and then your intuition and then start graphing it and seeing like what will actually happen, because now they're the same. Now if I set this 3x plus 5 and I set it equal to 0, what I'm going to get is, this is going to be a negative 5 as I flip it over, divided by 3, x is going to be negative 5 over 3. Now what that is, it's negative 1 point, I guess, 6, 6, 6, 6, 6, 6, and so on. Let's see it. So this is 9x squared, 30x, 25. Let's do that. Y is equal to 9x squared plus 30x plus 25. And let's see what happens here. So I'm going to graph this and check that out. So isn't that interesting? So in this case, you would thought, okay, well, it's going to cross the x-axis, right? There are two roots. But look what happens here. That these, okay, because you have factored it out, notice it's negative 1 point. So that point right there is 1.666. Now it's rounded it off a little bit. So it just touches the x-axis, and there's only 1 point where it touches it. It's exactly at that particular point. All right? That's what those two roots meant. Okay? And this should make you start thinking that sometimes you may not have any roots, right? You may be able to move this quadratic in such a way that it actually never crosses or never touches the x-axis. It might be above or maybe just fully below, and then instead of opening up, it might be opening down. This, the opening, which is the actual graph on its own. So you don't always have a factored form. And when you're learning about this in school, when it does factor, then there is a nice relationship with the intersection of the x-axis. But that's not always true in all the different graphs. And you'll come to those graphs a little bit later on. But this is just an introduction to let you know what these factored forms actually mean. Now, what about this last one? This last one right here is very, very odd because it's not a quadratic, and hopefully now maybe some of your intuition will tell you, okay, so what should happen? Now I'm using Z here, or Z, depending which country you're in. I'll stick with, let's say Z, so right here, so let me paste this. So it's a relationship, so there's no X, but that doesn't matter. Right, so you know, X is sure it's the x-axis. Now we maybe have a z-axis, right, and then the y is on top. So I can switch the z and then the x. That's okay. But the main idea is, what does this thing mean? What would you think if you would be thinking about these factors? What does this mean? First of all, how many factors, how many roots are there if I would set this to y is equal to 36z to the fourth minus 16z squared. Notice I factored out the 4 and the z squared, so this right here. And then I have two of these, which looks like it's a difference of squares there, right there, because it's 3z plus 2 and then 3z minus 2, okay, which indeed is a difference of squares. Now, from here, right here, from this z squared, well, when would y equal to 0? B is if z was equal to 0, because if you set z is equal to 0, it makes that entire expression 0. But there's two of them because of the fact that I have that, right? Because it's squared. So I have two of these. Okay, now I also have these, right? Because this one can be set to 0 as well, which means I'm going to have 3z plus 2, which is going to be set to 0. And then I also have this, which is 3z minus 2 can be set to 0. So what happens? Does this mean this will cross through the z 4 times? Or is it maybe going to touch the x-axis like it did in the perfect square right there? Would that maybe happen? Well, let's take a look and see how funky this will look like, right? Is it going to be a nice little straight kind of parabola-like, where it just kind of goes up and down, or maybe, you know, down this way? Let's take a look, right? So let's graph it. So it's 36 and minus 16. Let me remove this. This is y is equal to 36. Now, it doesn't matter if it's x or z, I guess. This is to the 4th. Minus 36 minus 36 z squared, and check that out. Well, isn't that interesting? All right, so this is what happens to this. Now, it's not actually 36. This was, I think, this was 36. This was 16. Okay, so it was something like that. There we go. Okay, now, well, that's funky. It looks kind of like almost like a tooth or something upside down. But notice that your intersecting points, so here is negative, I guess that looks like negative 2 over 3. This other one looks like it's positive 2 over 3. And then this, so remember that 0, so it looks like it just touches the 0 right there. And if I go back to these factored forms, indeed, if I would solve this, you would get z here, so bringing the 2 over on the other side, you're going to get 2 divided by 3, and indeed, you get 0.66666. And then this one would give you the negative 1. That's what these factored forms actually help us with. As you go through math and you continue, you know, you're going to be able to not only be able to factor, but you hopefully should know what the meaning of these things are. And when you graph it, meaning is it either touches or crosses the x-axis in some way, right? Or the z-axis or whatever axis you're using. I hope that this is helpful, and I don't know if your high school teachers, especially in grade 9 or 10, will go this far, but I think you should prime yourself with this and explore these graphs. So take a quadratic and then just graph it and then see like, what does this mean? Does it actually cross through it? Right, through the x-axis, or maybe it doesn't? It's certainly worth a try. Thanks for watching. We'll see you in a future video. Okay, bye everybody. Cheers.